Hello students. So in the last class we introduced the concepts of gradient of a scalar function and divergence and curl of a vector function. We also worked out few examples on gradient of a scalar function, how do you calculate it, and then we gave definitions of divergence and curl of a vector function. Today we will practice few more examples, but basically we will start with the examples on divergence and curl of a vector function, and we will see how we calculate them, and there are some results which are sort of important from these two concepts. So let's start with our examples on divergence and curl. So yesterday we introduced that if f is a vector function, then the divergence of f is basically defined as a gradient of this nabla dot f, and it is basically del f1 del x plus del f2 del y plus del f3 del z, where f is a vector function and it has three components, f1, f2 and f3, and each f1, f2, f3 are functions of x, y and z. All right. Similarly, the curl of f is defined as nabla cross product with f, and we have calculated via that determinant what it would look like. So in short, I can write the formula. So the formula would go like this: I times del f3 by del y minus del f2 by del z, then j times del f1 by del z minus del f3 by del x plus k times del f2 by del x minus del f1 by del y. You can be able to calculate with that with the help of that determinant. So this is basically our curl of a vector function f. Now, motivated from these two formulas or definitions, we will first start with our example 1. So let r is equals to x I plus y j plus z k. So when I write I cap, so that means it is a unit vector. All right, and then find divergence of r and curl of r. Right. So let us try to find solution. Let us try to find divergence of r. So divergence of r would go like this. We know that from the formula r has three components. So r1, r2, r3. So I can be able to write this formula del r1 del x plus del r2 del y plus del r3 del z. Now r1 is basically our x. So del del x of x is 1 plus del del of y is also 1, and del del z of z is also 1. So ultimately divergence of r is equals to 3 if r is given as this vector here. Now we will calculate the curl of r. So if I calculate the curl of r, then it will be I times del r3. So we just go through this formula here. So del r3 by del y. So this is basically our r3. So I can write r1, r2 and r3. Just for our clarification, you really don't have to write r1, r2, r3 at the bottom of these three variables. If you really want to, then you can say let r is equals to this, where r1 is equals to x, r2 equals to y and r3 equals to z. That you can do. So now our r3 is basically z. So del del y of z is 0 minus our r2 is y. So del del z of y is again 0 plus j. So del our r1 is x. So del del z of x is 0. Our r3 is z, and del del x of z is 0 plus k times our r2 is y. So del del x of y is 0 minus del del y of f1. So r1. So r1 is x. So this is again 0. So 0 times I, 0 times j, 0 times k. So ultimately we will get a 0 vector. So that means if r is equals to this vector here, then in that case our divergence and curl would be given in this fashion. So, divergence is 3 and curl is 0. So, that is how we basically calculate this divergence and curl. Let's consider a few more examples. So, just so we can be thorough in this thing. So, example let us say 2, and the example states that if our vector function f x y z is equals to x square y times I minus 2 x z times j plus 2 y z times k, then find first divergence of f, then curl of f, and then third one is curl of f. So, the thing is here curl is basically curl of a vector function is again a vector quantity. So, we can talk about its curl again. So, unless the quantity is a vector function is not unless the quantity is not a vector function, we cannot talk about its curl. But as soon as the quantity becomes or a function becomes a vector function, well, not becomes, if it is a vector function, then in that case we can always talk about its curl, and that is what is happening in this case. F is a vector function, but once we charge the curl, it again yields a vector function, and therefore we can again charge curl on it, which will again give us a vector function, and we can again charge curl on it. So, as long as the function or the we have a vector function, we can always talk about its curl. However, in case of divergence, we cannot charge divergence again, because the divergence of f would yield a scalar function. So, once we get a scalar function, we can talk about its gradient, but we cannot talk about its divergence. So, what would happen is when we charge divergence on a vector function, it would give us a scalar function, and then we charge a gradient, and once we charge the gradient, then it would become a vector function, and then we can again charge gradient as a divergence, and then it will again yield a scalar function. So, divergence gradient and so on. However, in case of curl, every time we can charge a curl on it. So, these are some small aspects of vector calculus, and I am pretty sure you may have got an idea that how to deal with these operators. All right. So, let us start calculating the first divergence of f. Okay. So, solution divergence of f, or let me start by writing. So, just start with writing here. So, I am just writing here f1 x y z equals to x square y, f2 x y z equals to minus 2 x z, and f3 x y z equals to 2 y z. All right. So, I just wrote the three components just for our sake. Now, we have divergence of f. I can write it in terms of notation as well. So, this is nabla dot f, and now in divergence we can go back to the formula. It is del f1 del x, del f2 del y, del f3 del z. So, del x of f1 is x square y plus del y of f2 is minus of 2 x z, and del z of f3, which is basically 2 y z. So, if I do del x, then this is basically 2 x y, and then here we do not have any y variable. So, the partial derivative would be 0, and here it would yield del z. So, 2 y. So, if I take 2 y common, then this will be x plus 1, and that is the required divergence of f. All right. So, this is what we obtain as a divergence of x, divergence of f. Now, we can calculate the curl of f. So, curl of f, I can write it as nabla cross f. I prefer to write in terms of these operators instead of writing in words. Now, we have I times Let us go back to the formula del f3 del y minus del f2 del z. So, del f3 del y. So, what is our f3? f3 is 2 yz minus del z of, in the formula, del f2 del z. So, what is our f2? f2 is minus of 2 x z plus j times, we have del f1 del z, we have del f1 del z. So, del z of f1, which is x square y minus del x of f3. So, del x of f3 is basically 2 yz, all right, and then k times del x, k times del x of f2. So, del x of f2 is minus of 2 xz minus del y of f1. So, del y of f1 is x square y, all right. Now, doing these partial derivatives is very simple, and I leave that task up to the students. So, here at the end you will basically obtain your answer as 2z plus 2x times I minus 0 component of j plus minus of 2z minus x square times k. So, ultimately we will obtain 2x plus 2z, or we can take this 2 common. So, let us not write 2 here, we can take 2 common times I minus of x square plus 2z k. So, this is our required curl of f. So, I can write it as implication sign. So, curl of f, and our problem 3 is curl of f, right. So, that means we basically have nabla cross product with nabla cross f. So, that means this is nothing but nabla cross 2 of 2 times x plus z times I minus x square plus 2 z k. So, here we have to identify our f1, f2 and f3, and then put everything back in this formula, and we would obtain our required result, all right. So, I am leaving that task up to the students. So, doing this is not complicated. So, you can identify the 3 components and just follow the previous formula, and that will give you the required result, all right. Now, we will consider some slightly different types of examples. So, let us start with them. So, here this says that determine the constant A so that the following vector field is solenoidal. So, what is that? So, v x y z equals to the given vector as x plus 3 y times I plus y minus 2 z times j and x plus a z times k. So, we have to determine this A here, so that this vector field will be a solenoidal, all right. So, this is our given vector field. Now, we know that from the definition in the previous class that a vector field is solenoidal when divergence of V is equals to 0. So, that means we have to make, so we assume that vector field is solenoidal, and we make divergence of V equals to 0, and from there we have to find out that for what value of A that divergence of V equals to 0 actually occurs, all right. So, we basically solve for A equals to some constant, and that will be the required the answer or the required value of A for which this vector field is solenoidal. So, let us start with calculating the divergence of V. So, here we can again identify our 3 components. V1 is x plus 3 y, V2 x y z is y minus 2 z, and V3 x y z is x plus a z. So, each component is a function of x y z. The correct way to write is actually v 1 of x y z, all right. However, you are allowed to write v 1, okay, or v 1 only as well, but the correct way to write is v 1 x y z, because it is actually a function of x y z, each component basically. Now, we calculate the divergence of v. So, divergence of v is gradient nabla dot v, and this will be del v 1 del x del v 2 del y plus del v 3 del z. So, del v 1 del x would be 1, then del v 2 del y is again 1, and del v 3 del z is a. So, that means we have a plus 2. Now, if we were a solenoidal, then divergence of v must be equals to 0, because that is the definition. And now, if divergence of v is equals to 0, that means a plus 2 must be equal to 0. So, from here we will obtain a equals to minus 2. So, for a equals to minus 2, v is a solenoidal field, is a solenoidal, all right. So, we start with the so after calculating divergence of v, we start with the assumption that we have a solenoidal field, and then in that case divergence of v must be 0, and from there we calculate a equals to minus 2, right. So, this is our required value for a, all right. Now, let us move on to our next example. So, our next example says that show that the following vector, so that the following vector is irrotational. So, our given vector is v x y z. So, this is our given vector function, right, sin y plus z times I plus x cos y minus of z times j plus x minus y times k. So, we have a given vector function or a vector field, and we have to show that this vector function is actually irrotational. So, from the definition of irrotational, which we learnt in the previous lecture, a vector function is irrotational when the curl of that vector function is 0. So, here we have to show that curl of v is equals to 0, and then it will be a irrotational field. So, let us first calculate or identify the three components, and then we calculate curl of f, all right. So, here our v 1 or v 1 x y z is sin y plus z, then v 2 x y z is x cos y minus z, and v 3 x y z is x minus y, all right. Now, we calculate the curl of v. So, curl of v is nabla cross v, and from the formula we have let us go back to the formula. So, it says del v 3 by del y minus del v 2 by del z. So, we can come back to the formula del v 3 by del y. So, del y of v 3 is x minus y minus del z of v 2. So, del z of v 2 is x cos y minus of z. We can use the third bracket, the bigger bracket actually, okay, times j, and then we have del x of then we have del z of f 1. So, f 1 is sin y plus z minus del x of f 3 is x minus y plus k times del x of f2, f2 is x cos y minus z minus del y of f1, f1 is sin y plus z, isn't it? All right. So, now when we calculate, so del y of x is 0 because x will be treated as a constant, and del y of y will be minus 1 minus del z of x cos y would be 0 because there is no z here, and minus of minus. So, this will be plus del z of z is again 1. Now, j times del z of sin y plus z. So, sin y is constant when we are differentiating with respect to z, and partial derivative of z with respect to z would be 1 minus del x of x is 1 and del x of y is 0, and k times del x of x cos y will be cos y and cos y, and del x of z would be 0 minus del y of sin y will be cos y and del y of z would be 0. So, basically we have 0 0 0. So, that means we have 0 times I plus 0 times j plus 0 times k. So, ultimately we obtain a 0 vector. So, from here we have curl of v equals to 0 vector, and this implies that v is an irrotational vector field. So, if the curl of v equals to 0, then the vector field is said to be irrotational, and we proved that the given vector function v is actually irrotational. So, all you have to do is remember these formulas, that if divergence of v is 0, then it is solenoidal, and if curl of v is 0, then it is irrotational, and you just have to verify, or if you were asked to calculate the value of a certain parameter for which it is either divergence or either solenoidal or irrotational, then you basically do what we did in the previous example. All right. Now, let's consider a few more examples. Some remarks are also to be addressed. So, let us consider our first remark. Suppose f x y z equals to a constant vector, right, a constant vector, then find gradient divergence of f and curl of f. So, the thing is solution, or the thing is, if f is a constant, then in that case a constant vector, then in that case when you charge this nabla operator has partial derivatives del x, del y, del z. Now, how it is being charged depending on whether you are charging the divergence or whether you are charging the curl. But whatever that vector function is, it will always be differentiated with respect to x, y and z. So, if your f is a constant function, it will always be differentiated with respect to x, y and z, and the minute you differentiate every component of that constant vector, it will lead to a 0 vector, because a constant vector differentiation of it will always be 0. So, regardless whether you are calculating divergence or curl, the answer would always be 0. In the first case it will be scalar 0, and in the second case it would be a 0 vector, because in case of curl we get a vector whose every component is actually 0. So, it is very simple to see, and I am leaving this result up to the student. So, divergence of f is actually 0 and curl of f is actually a 0 vector. So, these two things are quite straightforward to see, and I am leaving these up to the students. All right. Next so next we consider an example. So, next we consider an example. Evaluate curl of f, where our f x y z, it is a little bit interesting function, it is a slightly interesting function. So, e to the power x y z I plus j plus k. So, here we have to calculate the curl of f. So, let us go to the solution. So, curl of f, we know that the formula. So, here our three components are E x y z, E x y z, E x y z, because they are all same. So, I can write here, f 1 x y z so, here f 1 x y z equals to e to the power x y z, f 2 x y z equals to e to the power x y z, and similarly f 3 x y z is equals to e to the power x y z. So, now we calculate curl of f. So, curl of f would be I times it would be del y of f 3. So, del y of f 3 is e to the power x y z minus del z of f 2, del z of f 2 would be e to the power x y z, then j times del z of f 1. So, del z of e to the power x y z minus del x of f 3, f 3 is e to the power x y z plus k times del x of f 2, which is e to the power x y z minus del y of f 1, which is again e to the power x y z. So, now when we differentiate e to the power x y z with respect to y, so this will yield e to the power x y z times again we differentiate this one. So, times x z minus e to the power x y z times this will be x y plus j times e to the power x y z, and then this will be x y minus del x. So, this will be e to the power x y z y z plus k times e to the power x y z. This will be y z minus e to the power x y z, and this will be x z. So, now we will take e to the power x y z common. So, here it will be x times e to the power. So, this will be basically e to the power x y z common, and then we have x times y minus z times I plus y times z minus x times j, and this will be z times x minus y times k. Did I do it correctly? Y common, then this will be x minus z, okay, and that will be y minus x. All right. So, this will be y minus x, this will y minus x, and this will be x minus z. So, let us correct it. So, x minus z and y minus x, all right, x minus z and y minus x. So, this is the required curl of f for this given vector function f. Now, today we try to cover as many examples as possible. We will probably continue with our examples in our next class, and I look forward to it. Thank you for your attention.